This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
All right, let's get started. So yesterday we briefly reviewed one of the most fundamental laws governing our world and our I should say our understanding of the world, right? So that's the first law of the thermodynamics. Can everyone hear me okay? Not too loud or too... All right. The first law is mainly about energy balance. It says the energy has coming in and coming out of the system has to be balanced. So there could be other mechanisms which changing this balance. For example, if you have energy generated inside the system, or you have a storage mechanism inside the system to store a certain amount of energy. But in any case, all these different incoming flow, outgoing flow, and the source term, they have to add up together to be balanced. All right, so that's basically the first law is about. And but this is a law is not always being known. So many people does not really know this, and it's not being discovered until relatively 200 to 300 years ago. So there is an effort. People constantly try to develop something which can produce energy or generate energy without any source. So that's something called a perpetual motion machine. And even today, there is still some quite some effort try to develop this kind of machine. And I'd like to show you a video, just a 5 minutes video, just to show why that's not really possible to do this. Right. So that's a video coming from YouTube.
What if I told you I built a machine that creates energy? My ingenious design works like this. As the wheel turns, the coins fall in the slots so that one side of the wheel is open.
Turn on the volume.
What if I told you I built a machine that creates energy? My ingenious design works like this. As the wheel turns, the coins fall in the slots so that one side of the wheel is always heavier than the other, which would keep pulling that side down and the wheel would never stop turning. Without so much as a push, this wheel would spin forever.
Think about the possibilities. I could build a giant fleet of wind turbines that turn without wind to power the entire Earth. We wouldn't have to burn fossil fuels anymore. This could solve climate change.
So let's see it in action. Or not, because it doesn't actually work. You may have seen this wheel before, and there's a reason it doesn't work. Well, physics, but also friction here on the axle, which will eventually stop any wheel from continuing to spin. But then there's also gravity. So what I said earlier about one side of the wheel being heavier than the other was misleading because of the way gravity works on wheels. Imagine a regular wheel. Its center of mass is at the center of the wheel. Now imagine a wheel with a single coin in it. It might swing back and forth a couple times, but it won't rotate. Add a second coin, add a third coin. The wheel swings back and forth, slowing down until it stops where the center of gravity is at its lowest position. Always. So the unbalanced wheel will swing back and forth like a sad pendulum until friction wins. This wheel is a perpetual motion machine, a device that is supposed to move without any energy.
But by far the most persistent dream of inventors has been to get something for nothing. That is, to create a machine that will start itself, overcome all friction, and still have enough power left to do useful work. In short, perpetual motion machines.
In countless instances in history, people have claimed that they've made a perpetual motion machine. Bhaskara's unbalanced mercury wheel in the 1100s, Zaimara's self-blowing windmill in the 1500s, the capillary bowl where capillary action forces the water upwards, the Oxford electric bell which ticks back and forth due to charge repulsion, and so on. In fact, the US Patent Office stopped granting patents for perpetual motion machines without a working prototype. The reason you've never heard of Cox's timepiece and you don't power your smartphone with a capillary bowl is that perpetual motion machines are the snake oil of physics. They are impossible. This is the classic drinking bird toy. It tips itself into a glass of water and then rights itself and then tips again over and over, looking forever thirsty. Where's the source of energy? At room temperature, inside the bird is part liquid and part vapor. The bird contains a substance called dichloromethane, the same stuff in this little toy, which boils at a much lower temperature than water. When the bird dips its beak into the water, the bird's top cools down. Because of the ideal gas law, PV equals NKT, the pressure in the tube at the top of the bird is lower than the pressure in the bottom of the bird. This pressure difference pushes the liquid into the top of the head. The toy gets top heavy and tips over. When the bird tips over, the bottom of the tube is exposed to the vapor, which rises up and pushes the liquid back into the bottom. The bird stands up and the cycle continues. But it's not perpetual motion. There is an energy source making this bird drink over and over, but it's hard to spot.
Yep, I'd like to stop here. And so the question here being asked is, there is an energy source actually driving the bird to tip and coming back. Any idea? So we will learn that in a minute, but any idea?
There is a hot reservoir transferring energy to the cold reservoir.
What are the hot and cold?
The hot source maybe
From where?
water.
That's the right direction of thinking. So where is hot and cold reservoir? Yeah, that's pretty close. The ambient energy, which ambient actually serve as the hot and the cold at the same time in this case. All right, that's good.
The energy source for the bird is the ambient heat in the room. Bear with me. The water cooled the bird's beak, creating a temperature difference between the top and bottom, and that caused the pressure difference that made the liquid flow to the top and tipped the bird over. When the pressure equalized, the top and bottom of the bird became the same temperature, but slightly cooler than it started out. Then the room warms the bird up again, and that's where we see our energy source. This back and forth between pressure and temperature is what causes Earth's weather. And though it seems like weather and wind and storms never stop, they're powered by the sun's heat. So even Earth's weather isn't a perpetual motion machine. Now, there's a more fundamental reason why these machines are impossible, and it's called the law of conservation of energy, which states that energy can neither be created nor destroyed. Energy never comes for free. If you see a machine producing motion, heat, light, or another form of energy, keep looking for the energy source. I repeat, keep looking for the energy source. So now you know. If anyone tells you they've built a perpetual motion machine, tell them to peddle their wares elsewhere. Thank you so much for watching.
It's all very simple. And so are you if you think it'll work.
You can't get something for nothing.
Yeah. So that's the main message coming out of here. You cannot get something for nothing. You have to, energy has to be balanced. So the in and out, or either generation, storage has to be balanced. And for this type of machine, if you want to know how it works, generally there are two ways. One is you give it certain energy to start with, then during the process there is very little loss. So for example, for those unbalanced wheels, when it's turning, it must sitting on X, which is very well lubricated, so that wheel can run for a long time. So the loss is very small. Or there is a very subtle source to supply the energy, just like the drinking bird. So again, the principle is energy has to be balanced, but somehow in certain cases it can be confusing. But stick to the first principle. All right. So the first law, we look at the equation of the first law, which is Q heat minus work equals to change in the internal energy. So that's applied to a closed system. And the closed system, we said, is a simple compressible system, which is the system all the system we encountered in this subject. And if you have an open system, which you have a flow, steady flow, constantly going in and out of the system, there is another equation for that. In this case, because when the flow going in and leaving the system, it requires energy to be pushed in and pushed out. So there is a term called flow energy, which stands for the delta PV. And combine these two, you get the delta enthalpy. All right, so this applied to the flowing system. Or you can refer to it as open system. So this equation in certain textbook being called a non-flow energy equation, and this one is being called a steady flow energy equation. All right. We said work and heat, they are pulse function. Their change determined by which route from one state to the other. So to determine them, you really needed to know how the process goes. But the energy term, energy and enthalpy, they are the state function. So they can be more directly, more straightforwardly calculated. So we know that du changing the internal energy can be written as Cv dt, specific heat measured under constant volume condition, and the dH can be written as the Cp dt. Right? That should coming from your previous learning. So the Cp and the Cv, they are the specific heat measured under different conditions. And for gas, there is a clear difference between these two. So if we're talking about ideal gases, which are the gas we deal with here, ideal gas has a different Cp and the Cv. Cp minus Cv equals to the gas constant. And this gas constant can be calculated from the universal gas constant divided by the molecular weight of that gas, right? The universal gas constant, 8.314 joule per mole per Kelvin. Right, so for ideal gases, Cp, Cv are different, and their ratio is called gamma, ratio of the specific heats. So because Cp is larger than Cv, so gamma is always larger than 1. And there is some theoretical values has been known for this gamma. So if you have a monoatomic gas like helium, argon, for those noble gases, the gamma is 1.67. Basically, it's 5 divided by 3. It's coming from the statistic thermodynamics. But that's not really, we don't really remember those here. For condensed matter, solid and liquid, the Cp and the Cv are very similar. So in that case, basically when you want to determine the changing du and the dH, they are basically the same. Right? Their internal energy, regardless is internal energy or enthalpy, they are the same. very similar, at least I should say. All right, so that's the simple relations that we want to be aware of, and that's mainly coming from the first law. Again, the first law is about energy balance. So we said energy can be converted, thermodynamics is about energy being converted in different forms, then being transferred in and out of the system, right, with its surroundings. And the first law is just say everything has to be add up to be equal. The source term and the sink term has to be add up to be equal. And whether this form of energy is in terms of heat or in terms of work or in terms of chemical energy, it doesn't matter. As long as it's an energy, one form of energy that add up together has to be equal. That's what the first law is about. So if I have for example, if I have 1 kilojoule of heat, that equals to 1 kilojoule of work. That's required by the first law, and that actually being proved by the person called Joule, James Joule. His name being used to name the unit of the energy, and he it's the other way. He actually designed an experiment to prove this. So his experiment, at that time, people doesn't really know the first law, saying that 1 kilojoule of work equals to 1 kilojoule of heat. People doesn't really know that. So he did an experiment to prove that concept. So energy in different form are equal, at least in terms of work and heat. So this is his experiment. All right. So what he did is he has a weight, like has a string attached to a string and going through a pulley, and this pulley is driving a pedal, and this pedal is in a water tank. All right. The water is with no mass inside the tank, and you have a thermometer to measure the temperature. So by his experiment basically is when this weight is going from going through a certain distance in terms of height, you can have an energy which is potential energy change in terms of mg delta h, right? So based on the distance this weight traveled, you can calculate how much potential energy it released. And then this energy, assume there is no energy loss, so he designed the system so there is very small friction. So design, all this potential energy is going here to become this kinetic energy, which is driving this pedal. And when this pedal is turning, the energy, kinetic energy is being converted to heat or thermal energy to the water. And that one can be measured through the thermometer. So from here you have the, this is the weight, mass of the weight. And here you can have the energy which is Q equals to mc delta T. So that's mass of the water. Can you see? Yep. So these two, they found they are equal. So I mean, both can be accurately measured in terms of temperature and with a known Cp and a known mass of water. So found that these two are equal. Basically proved that the 1 kilojoule of work equals to 1 kilojoule of heat. All right. So that's a pretty famous experiment called the Joule experiment. Basically prove the first law. So that's the, we want to mention this because there is a big difference in terms of second law. If we're talking about the second law, second law is saying that even though in terms of Joule they are the same, in terms of the capability to do work, they are not the same. So if I have 1 kilojoule, let me just be 1 kilojoule of heat that not equals to 1 kilojoules of work. That is in terms of the capability to do work. So 1 kilojoule mechanical work, if you already have there, it can be directly converted to useful work in this sense. But if you have 1 kilojoule of heat that is available there, it cannot be all converted to mechanical work. So this is what the second law is about. Second law, the essence of second law basically is saying that different form of energy are not equal, right? Like the first law, everything add up together, being the same. So in that process, all type of energy are being equal. But if you consider the capability to work, different type of energy have different quality, but different capability to do work. So that's mainly this second law is about. And there is a, maybe just add a note. Should say different energy forms are of different quality. Certain energy form are considered as high quality. Mechanical certainly is one. Electrical is also one. Chemical, generally considered pretty high quality. The thermal energy actually is the lowest quality of energy in terms of doing work. So that's the general idea, and there is a two statement. So when people discover this, again, this is not known before. This is through numerous or many experiments and experience. People summarized this type of law. One is called Kelvin-Planck's law. I put it here. So that one saying that it's impossible for any engine working in a cyclic process to draw heat from a single reservoir and convert it to work. All right, so let's draw a schematic to show this. All right, so this one saying that if you have a cycle, like if we consider our engine is running on a cycle and going from this direction and walking between two temperature reservoirs. One is hot, one is cold. Right? So if we have the process running so that the cycle is picking up heat from this hot reservoir, which we said picking up the QH. So this is like when you have a combustion process, combustion happens to convert chemical energy to thermal energy, and then you're picking up the heat from the process. Then you want to do work, right? The purpose of engine is to do work. The Kelvin-Planck statement is saying that the QH is not equals to work. Actually, the QH much larger than work, and there is always certain amount of heat or some certain amount of thermal energy that cannot be used in the process, then need to dump into the low temperature reservoir. So that's why it's saying that there is impossible for any engine working in a cyclic process to draw heat and convert it to work from a single reservoir. You must have a hot and a cold reservoir. Picking up the heat from the hot and then doing some work, then you must dump certain heat to the low temperature reservoir. You cannot convert all those heat from the high temperature reservoir to work. So that's the statement of the second law by the Kelvin-Planck's statement. All right, so the balance here actually is a QH minus QL equals to W. You only can convert the difference between these two heat stream to work. Right? And that's the one. And the other one actually is working in the opposite manner from the Clausius statement, that it's impossible for any engine working in a cyclic process to produce no effect other than transfer the heat from a cooler body to a hotter body. So in this case, consider if you want to remove a certain amount of thermal energy from a cold reservoir and dump it to the hot reservoir. This is like a refrigerator working principle, right? So in this case, if we draw the schematic again, so you have the cold and hot, and the work engine is running in an opposite way. I mean, we call the engine basically is a thermodynamic cycle, right? So in this case, if you want to pick up certain energy from the cold reservoir, and you want to move it to the high temperature hot reservoir, this case is saying that the QL cannot equals to QH. You have to input some additional work in order for this case to happen. Even though the what you want to remove to the QH is only 1 kilojoule, you cannot completely dump that 1 kilojoule to the hot reservoir. You have to input some useful work and dump the sum of these two to the hot reservoir. So in terms of the equation, that's the QH must equals to QL plus some useful work. So this is a two statement, basically saying the same thing. People state the same principle, which is coming from the different perspective. And because of the second law, you will never see a car exhaust as cold as ambient. Engine exhaust is always hotter than the ambient. That is due to this QL will never be zero. The QL must be positive to dump into the cold reservoir, which is ambient, in order for this process to happen. And also, when you have a fridge, if you ever pay attention in terms of how refrigeration cycle works, a refrigerator always requires a compressor in order to work. And that compressor is in order to provide this additional external work in order to move the energy from the cold reservoir to the hot reservoir. Right, we'll discuss more when we're talking about the specific cycles there. But the second law is universal, and it's always show itself in certain way. All right, so that's the statement. All right, in terms of study, we always need the equations. So the mathematical expression of the second law is has been developed. So that's called the Clausius inequality. Basically, it's saying that if you have a cycle, you have a process, a cycle, which is reflected in this circle here. So you integrate the total heat transfer over a cycle. There always will be no greater than 0, either negative or equals to 0. So that's the expression of the second law. For most, no, I shouldn't say for most, for all practical processes, the unequal sign will apply. And when you only have some ideal process called the reversible process, the equal sign will apply. So in reality, all the process will going in the way. If you have a cycle, all right, which stand by the circle here. If you have a cycle, this you always will be losing heat to the surroundings, right? And it's similar to the case. I should say all the real process or practical process are irreversible. That's just like the time. The time is always going in one direction. You cannot go back in terms of time. So you can consider the process along the time is always irreversible, right? So that's part of reflected to the all the practical process are irreversible. But we do have an ideal case. So for reversible process is something saying that it happens, the process happens very, very slow. I mean, again, it's an ideal case, very, very slow. At any point, if you want to go back, you can go back, and the state will go, I mean, the whole situation will go back in terms of the previous condition. So that only happens in ideal condition again. So for reversible process, this equal sign can apply. Equals to 0. All right. So now people recognize there is something new here. So if you have a property, if you're going through a cycle, which means the start and end point are the same, right? Going through a cycle, and its change becomes 0. There is no change, which means this should be it's a state function or it's a past function.
State function.
It's a state function because its starting and end are the same, and for the state function there should be no change. So people realized if you, for a reversible process, this property now become a new state function. All right, and that new state function is later being defined as the entropy. And entropy is using the capital S to stand for it. Entropy is similar to the internal energy or enthalpy, although they have different units, but it's an extensive property depending on how much mass inside the system. So I should say this is a for a reversible process equals to the ds. That's how the entropy is being defined. Entropy is always challenging concept in terms of understanding. It's different from energy, but people has put some physical meaning to it. In terms of straightforward way to say it is entropy is a disorderliness of the system. So how disordered the system is, you can characterize that using entropy. So entropy can be understood as a measure of disorderliness. So, in other words, it's a measure of freedom in a system. So, if the system has the component or the constituent in a system has a lot of freedom within the system, If there is more, which is the system is more disordered, then you have a more entropy in the system. So in that regard, if we increase in temperature, how the entropy will be changing? Well, going up, because there is more freedom in terms of the gas molecule, or whether it's a solid or liquid, for the molecule inside the system to move around. So entropy will go up. How about pressure? When the pressure going up, it will suppress the movement of those molecules inside the system. The entropy should go down, right? And if you have a phase change, for example, if you have liquid water to become a steam, to become a vapor, that process will give you a change, a higher entropy, right? And the other way would reduce the entropy, right? So this is the, if you understand the process, entropy as a disorderliness of the system, when this system condition changed, you can have a general understanding, quantitative way how they are going to change. All right. One thing I should add before we move to the equations. So if you have an isolated system, isolated system is a quite a special system. It's an exact type of the example for exact isolated system does not really happen very often. You can consider a universe as a whole, as an isolated system, because it's saying that the system should be closed system and adiabatic, has to satisfy two conditions. Basically saying that this is isolated system. It doesn't have mass exchange with its surroundings, also does not have energy exchange with its surroundings, right? So it's closed and adiabatic. So for isolated system, people already find that the entropy of that system is always goes up. So this something has been proved, can be actually being proved pretty easily, and that's I think that's the first tutorial question in the first tut. So there it will be demonstrated why for isolated systems entropy always goes up. So to understand this actually being considered as a part of the nature. So by nature, things always goes to have more disorder. Things have become more disordered. So if you just move into a new place, everything is tidy and the things are in the place they should be, right? But over time, what happened? The things will become, in general cases, all right? I'm talking about general cases, it will become messier and messier, right? The things will be laying around and certainly not always at the place they should be. So that's, you can thinking that's the second law is in action. Although your room is not necessarily an isolated system, but in general, by second law, saying things are just become more and more disordered. And if you want to reduce the entropy, you have to put in extra additional effort in order to correct this trend. All right, so that's a tutorial problem, which we are going to prove that. So entropy is a new state property, a state function. So how do we calculate it, right? So we know how to calculate the internal energy and entropy using the equation, where is the equation? Using the equation here. Using the equation which is CV and CP. How do we calculate another state function which is entropy? That's the things we're going to discuss here. Or more correctly, changing the entropy. Again, similar to the energy term, only change matters because the absolute value is really depending on what the reference state that you choose. Right. To determine the changing entropy, we combine the first and the second law. From the first law, we have Q minus W equals to delta U. So if we consider this is a closed system, all right, consider the closed system, and we consider it's a reversible process happening to this closed system. For the reversal process, then we can express the heat in terms of the entropy. T ds. So this only because you have the Q for a reversible process. Then you have the Q equals to TdS. For irreversible process, that's not they are not equal, right? And then if we consider the work term, there is only boundary work being done. Boundary work means, for example, you have a setup of a piston and a cylinder. So when the gas inside the system becomes hotter, it will push the cylinder to move. That's changes the boundary of the system, and that work is called the boundary work. It does not involving shaft work or other type. Does not involving shaft work. Does not involving electrical work. So it's just the work is related to the system boundary is expanding or shrinking. So in that case, we can write the work as a P dV. The pressure push the volume change. And then we have the change in internal energy. We can write in terms of Cp dt. Right? So I should be more careful in terms of the signs here. So I want to write in terms of the mass specific form. So in other words, this ds is a capital S divided by the mass already, and this volume is a capital volume divided by the mass. And so here I don't need to write mCp dt there. All right, so if I do this, I can, with a few steps of derivation, we can get the equation to calculate the entropy change. All right, so we have the T ds P dV equals to Cp dt. Then I have the ds equals to Cpt dt plus Pt dV. All right. So I want to rearrange this term using the ideal gas law. So from the ideal gas law, we have PV mRT. Right? So if I move the mass to here to make it to be a volume specific mass, then I can write the PT in terms of P divided by T, R divided by the V. This is the mass-specific volume, right? Then I can bring it to here, Cpt dt plus Rv dV. So then I got the differential form in terms of entropy equals to the this. What I need to do is just integrate from one state to the other. Then I have the S2 minus S1 equals to Cp log T2 T1 plus R log V2 V1. So that's the first equation that we come up to determine the entropy change. So this equation is called the Gibbs equation. And this equation actually we are going to derive a second form. The first form is like this. Basically the change for entropy from one state to the other can be determined from the change in temperature, which can be relatively easily determined, right? Temperature from one state to the other can be determined times the specific heat, then the change in the volume from the first state to the second state, then times the gas constant. So then this entropy can be calculated, right? From properties that can be easily determined. The second form of the Gibbs energy that's pretty similar. It's based on the same principle, except it dealing with the entropy. Sorry, I think I made a mistake here. So this should be CV, right? Should be CV rather than CP because we're dealing with internal energy. The second form, I can quickly go through them. Again, we have the Q minus W equals delta U. In this case, I write the delta U in terms of the enthalpy minus delta PV. Right? That's something I can do because H equals to U plus PV. Then I remove the Q. I can still write in terms of the T ds for a reversible process, and then the delta H P. Sorry. More specific, dH minus P dV minus V dP, then plus the work term. The work term I move to there, we'll have P dV term. So the point is, these two got cancelled. I only deal with dH minus V dP there. Right? Then follow the similar procedure I just shown here. I can get the ds equals to Cp log T2 over T1, then minus R log P2 over P1. So this one is also called the Gibbs equation. So this one, basically that's based on the same principle, just expressed either in terms of temperature volume or temperature pressure. So the purpose of the Gibbs equation, S2 minus S1, right? So the purpose of the Gibbs equation again is to calculate the entropy change, which is a pretty abstract concept in terms of the more common properties of the system. And from here, you can confirm what we discussed earlier in terms of when the system condition change, how the entropy is going to change. So from here, you can see that if the temperature goes up, this term will become higher, right? The entropy should go up. If the pressure is the P2 divided by P1, if the pressure goes up, this term will become larger, so the entropy change will change in the negative way. And if you're looking at here, this is the volume. The volume have a plus sign in front of it. If the volume of system, the volume change, which means there is more freedom for the species inside to move around, then the entropy also should goes up. All right, so that's a theory confirm our intuition. All right, so that's all for today. Let's continue Friday. This is a volume. This is not this is like a normal volume.
It's not mass.
But this is mass.
It's mass. So from here to here with the
So here is the mass specific.
Mass.
So here already have the V divided by M. This one is not that one. So that one is this one is V divided by M.
So what is this for?
So this is a mass specific volume.
Mass specific volume.
Basically it's a volume divided by mass. It's called mass specific. You can consider that's the inverse of density. So it's a 1 divided by density.
Okay.
Because mass divided by V
is the density of speed, like.
But this is the inverse. It's 1 divided by density. V divided by M is because density is M divided by V. So this one is 1 divided by density. You have a question?
Yes.
Yeah, go ahead.
When it's a reversible process, so this inequality equals 0,
Yeah.
why does it mean that's a state function?
Why it means state function? So the definition of state function is saying that if you have from state 1 to state 2,
Yeah.
the change of this state function only depending on its initial and final states.
Yeah.
Right?
Not the path.
Not the path.
Yeah.
Yep. So if you have a cycle, here we're talking about a cycle. If you have a cycle, which we basically saying the start and end are the same.
Oh, okay.
So
Doesn't matter where it goes.
Yeah, if the state function, if it is a state function, then it's always 0. The change of the state function is always 0. So that one,
yeah,
if you have
okay.
a reverse process, then that's 0. Then that can be considered as a new state function.
So if it's any cycle, wouldn't it always be 0? Or is it just reversible?
Only reversible you have 0. So if it's a state function going through a cycle, it's always 0.
Yeah.
But the total energy, I should say total energy. If it's not a state function, if it's heat and work, it's definitely not 0. Going through a cycle.
Because your work is being outputted.
Yeah.
Okay.
Yeah.
Right.
The sum of them has to be conserved in terms of First law.
Yep.
But those changing work, changing heat, definitely is not 0.
No. All right. Gotcha. Cool. Thank you. That's all.